Hello everyone. We are given a closed loop system with the plant transfer function Gp of s equals 14.4 divided by s times 1 plus 0.1 s and the compensator transfer function Gc of s equal to 1. It is also given that for a unit step input, the output response has damped oscillations. We are asked to find the damped natural frequency in radians per second. To know more about the concepts used to solve this problem, kindly refer the NPTEL Control Engineering course, Week 3, Lecture 3 by Professor Ramkrishna Pasumarthy of IIT Madras. We will be using the following concepts to solve this problem. The general form of a second order transfer function is T of s by R of s equals omega n square divided by s square plus 2 zeta omega n s plus omega n square, where omega n is the undamped natural frequency and zeta is the damping ratio. The damped frequency of oscillations would be omega d equals omega n times root of 1 minus zeta square. Let us start solving the problem. So we are given a block diagram with the compensator and then a plant, the output, and then is the reference input, then there is a feedback. So we are given Gp equals 14.4 divided by s times 1 plus 0.1 s and Gc equals 1 and the feedback is also unity. So let us first find the closed loop transfer function. So C of s by R of s equals G by 1 plus Gh. Here G is the forward path transfer function and H is the feedback path. So this will be equal to, so here the forward path has two blocks in cascade. So we can just multiply the transfer functions. So that will be equal to Gc times Gp divided by 1 plus Gc times Gp times H. So here Gc and H are equal to 1. So we'll substitute Gp. So that will be equal to 14.4 divided by S times 1 plus 0.1 S, the whole divided by 1 plus 14.4 divided by S times 1 plus 0.1 S. Now you can simplify this by taking the LCM. That will be equal to 14.4 divided by 0.1 S square plus S plus 14.4. Now you can write this in the standard form. You will get E of s by R of s equals 144 divided by S square plus ns plus 144. So there are two ways in which you can solve now. So the first method is to compare it with the standard form of the second order system. So the standard form of a second order system is omega n square divided by S square plus 2 zeta omega ns plus omega n square. So now if you compare, you can find omega n square equals 144 and 2 zeta omega n equals 10. So these are the coefficients. So now you can find omega n equals 12, and if you substitute in this, you get zeta equals 10 divided by 2 omega n, which is equal to 10 by 24. So that turns out to be 0.4167. Now we'll find the damped frequency of oscillations. Omega d equals omega n root of 1 minus zeta square, so which is equal to omega n is 12 times root of 1 minus 0.4167 square. So when you compute this, you get this as 10.91 radians per second. Now the second way. So in the second way, the characteristic equation of the system is s square plus 10s plus 144 equals 0. So now this is a quadratic equation with two roots. We know that the roots of this equation are minus zeta omega n plus or minus j omega d. So now if you solve this quadratic equation, you can find omega d as its imaginary part. So we can use the quadratic formula, that is s equals minus 10 plus or minus root of b square, that is 100, minus 4ac, that is 4 times 144 divided by 2. So that is equal to minus 5 plus or minus j 10.91. So now you can see that the damped frequency of oscillation omega d is in the imaginary part. So now you have omega d equals 10.91 radians per second. So the correct answer is 10.91 radians per second. Thank you.